must. Yeah.
I'll have to try some of that.
Good afternoon. Let us start our lecture today. So as I promised, today I'm gonna review for you the Cauchy equation. Right?
Excuse me, sir. Do we have a homework assignment before the test or just the practice test?
We have only the practice test.
Okay.
And we will do it after this review.
All right.
But I mean, the test, as you can see from the practice test, is very similar to what we did in class. Right?
All right.
So basically, if you do well those things, it's gonna be fine. All right. So today we're gonna review about the homogeneous Cauchy equation. All right, so this equation takes the following form. You have a x squared y second plus bx y second plus cy is 0. This is the differential equation that we need to solve. This is completely different from what we reviewed before. So before you have a y second plus by prime plus cy is 0, and so the characteristic equation in that case will be a squared plus br plus c is 0, right? This is the equation that we reviewed before. So in this case, all of the coefficients are constant. A, B, C are constant. So in the case that A, B, C are constant, the characteristic equation is standard, A squared plus BR plus C, right? And then you consider 3 cases, right? There are 3 cases. So case number 1, so you have to define a delta function which is b squared minus 4ac, right? And case number 1, delta is positive. When delta is positive, you have 2 solutions, 2 roots for the characteristic equation. Right, so you have R12 will be minus b plus or minus square root of delta over 2a. Right, so this is the table that we wrote before. So case number 2, when delta is 0, you also have one double root. R will be minus b over 2a. In this case, the solution will be c1 e to the r1x plus c2 e to the r2x. Right? In this case, the solution will be c1 e to the r1x plus c2x e to the rx. It's good, right? And this is the what we usually use, for instance, in the previous midterm. And case number 3, delta is negative. You also have 2 roots, right? So R12 will be minus b plus or minus I square root of the absolute value of lambda delta over 2a. So in this case, you have c1 e to the minus b to ax cosinus of square root lambda over 2ax plus c2 e to the power minus b to over x sinus of square root of lambda over 2ax. All right? I explain again. This is what I wrote for you in the previous class. You have a second order differential equation with constant coefficients. So A, B, C are constant. What you do is you write out a characteristic equation, AR squared plus BR plus C is 0. You consider the delta, B squared minus 4AC. There are 3 cases. Delta is positive. This characteristic equation has 2 root minus B plus or minus delta over 2A. And then the solution of this guy should be C1 e to R1x plus C2 e to R2x. If delta is negative, is 0, this characteristic equation has a double root, which is minus b over 2a And then this gives you C1 e to the Rx plus C2x e to the Rx, right? In the last case, delta is negative, you have two roots, but they're both complex numbers, right? Minus b first or minus I square root delta over 2a, and then you have this and this. Now, this is what we review. Today I'm gonna review for you one more thing in which the equation has non-constant coefficient, right? So in this case, you have x squared in y second and x in y prime plus cx. In this case, a, b, c are also constant. Right? So the characteristic equation in this case will be the following. It's gonna be a r squared plus b minus a plus c is 0. Right? So once you put the x into the equation, the characteristic equation change. So here I put x squared to x second and x squared to y second and x to y prime, in which a, b, c are constant. So the characteristic equation looks similar, except that here you don't have b, you have b minus a, right? And then you also consider the delta. So the delta will be b minus a squared minus 4ac. All right? So in this case, the delta will be the coefficient of r squared minus 4 times the product of the coefficient of a and c, right? So this is the review on ODEs. And this is in the book of Haberman. Introduction to differential equations, right? Introduction to differential equations. Right, so in this case, the delta function will be b minus a squared minus 4ac. Then we also have two cases. Case number one. So if delta is positive, what happens when delta is positive? How many roots do we have for the? Yes?
You have to,
What are they?
maybe like minus b plus or minus square root of delta over 2a.
Can you say it back to paper, please? So in this case, you also have two roots, right? Two roots, but you don't have minus b. You have minus b minus a plus or minus square root of delta over 2a, and this is R1 and R2, right? So this is standard quadratic form. So if you have a r squared plus b minus a r plus c is 0, I consider delta to be the square of this guy minus 4 times the product of the first and the last guy. If delta is positive, this equation has two roots, minus b minus a plus or minus square root delta over 2a, right? So the two solutions will be so what is the form of the solution in this case? Yes?
C1 e to the R1x plus C2 e.
No. The e works only for this case. For this case, you have to change a little bit. Who can give a better guess? This is something similar, but it's not exponential. So, because exponential is only for this case where all of the coefficients are constant. Here, you have polynomials in the coefficients, right? So exponential, yes?
It is C1 R1x, C1 times R1x plus C2 times
Now x to the power R1. Right, so it's going to be C1 e to x to the power R1 plus C2 x to the power R2. Right? So this is the solution. when you have polynomial in the form of the equation, you have to play with polynomial, right? Because here you have polynomial in x squared. So you have polynomial ax squared in the coefficient of y second, bx in the coefficient of y prime, right? Which means that here you're gonna have to put polynomials, right? You have c1 x to the power r1 plus c2 x to the power r2. Case number 2. When delta is 0. What happens when delta is 0? Yes?
We have repeated roots.
Yes, what is it?
R is going to equal A minus B over 2A.
Can you stand the back of paper, please? So in this case, you're going to have a double root, right? The double root will be minus B over A over 2A. Alright, so it's going to be A minus B over 2A. And then in this case, y will be C1. So what is the first term here?
X to the R1.
Yes, can you sign the back? So here you have x to the a minus b over 2a. And then the second one will be log x, x to the a minus b over 2a. Right? Right, so this is similar, but you have to remember that you have to replace into the exponential by the polynomial, right? And then in the case that you have the double root, you also replace x by log x, right? So here you replace exponential by polynomial, and in this case you replace x by log x. All right, case number 3. Delta is negative. What happens when delta is negative? How many roots do we have? What are the 2 roots? Yes?
C1.
I want to know the 2 roots of the quadratic form first.
It would still be minus b, b minus a, and then plus minus like I of the absolute final delta over 2a.
Yes, can you stand the back of paper, please? So in this case, the 2 roots will be the same, but you have to take into account the fact that you have you have something negative, right? So this is like this, and this is written like minus b minus a plus or minus I square root of lambda, the absolute value of lambda over 2a. All right? Right? So in the case where delta is negative, you still have the 2 roots that you, like in the first case, is going to be minus b minus a plus or minus square root delta over 2a. But in this case, delta is negative. So what you do is that you put an I square root of delta over 2a. Right? Right. So in this case, the solution will be C1 x to the power. Someone can guess what is the form of the solution? Yes?
So, I heard someone else.
You want to guess?
Me? Oh, C1x to the power R1 times cosine square root of delta over 2a.
This is close, right? Can you stand the back of it? Yes?
Oh, in the cosine and sine, you need a log x.
Right. Can you stand the back of paper, please? So you're gonna have x to the power b minus a over 2a, right? And then you have cosinus, and then you still have square root delta over 2a. But instead of x, you're gonna replace it by log. All right? So you replace the exponential by the polynomial, and then the x by the log x. Right? So then you have c2 x to the power minus b over minus 2a over 2 sinus of square root of delta over 2a log x. Right? So you replace the x by the log x. And you replace add the exponential by the polynomial. Right? I explain again. For this kind of differential equation, the characteristic equation will be changed. The characteristic equation in this case will be a squared plus b minus a plus c. So the change will be this term, right? So in comparison with this term. Then you also have three cases. The first case is that this delta is positive. So the delta in this case will be b minus a squared minus 4 times ac. So in the first case, delta is positive. This characteristic equation has two roots. Minus b plus or minus square root of delta over 2a. And then in this case, the solution will be c1 x to r1 plus c2 x to r2. Right? So you just replace the exponential here by the polynomial. In the case number 2, if delta is 0, then you want to have a double root minus b over minus b minus a over 2a, which is a minus b over 2a. Right? So you want to replace the exponential here by the polynomial, and then you replace x by log x, and that's it. Right? So the exponential will be replaced by the polynomial. Case number 3, delta is negative. When delta is negative, you still have the two roots r1, 2, which is minus b minus a plus or minus square root delta over 2a. But in this case, delta is negative, and because delta is negative, you have to take the square root of a negative number, which means that you have to introduce an I here, right? The two solutions will be the same, except that you replace the exponential by the polynomial and the sinus and x by the log x. Questions? Right. So now I'm gonna explain to you briefly why you have two different characteristic equations. Any erase? So in the first case, you have a. In the first case, you have a y second plus by plus c prime plus c is 0. Right? How do you find the characteristic equation? Where the characteristic equation comes from? We discussed this last time in one of the review classes.
Should it be cy?
Cy, yes. Inside back the paper, please. So, where's the characteristic equation come from? We discussed this once. Yes?
Isn't it the method that we use in differential equations, y equals e to the RT?
Yes. Can you send back the paper, please? So, in the previous class, we're gonna guess the solution of the form e to the x, right? So, so you guess that the solution is of this form, so then y prime will be e to the x, and y second, so y is a function of x, remember that. So y second will be square e to the x. Now you plug everything back into the equation. Then you have a square e to the x plus b r e to the x plus c c e to the x 0, right? So the idea of solving a second order differential equation with constant coefficient is that you guess the solution should be of exponential form. All right. So if the solution is of exponential form, I'm gonna take the first derivative. This gives me r e to rx. The second derivative gives me r squared e to rx. Right? You plug everything into the equation. Then you get ar squared plus br plus c e to rx, and this is 0. So ar squared plus br plus c has to be 0. And this is the characteristic equation, right? This is the characteristic equation. And if we can find R1 such that AR1 squared plus BR1 plus C is 0, then A ER1x second plus B ER1x prime plus C1 C e to R1x is 0, which means that ER1x is a solution. Right? So after I guess the form of the solution to be e to rx, I plug it to the equation, I get ar squared plus br plus c is 0. Right? So now if I can find R1 such that this is 0, which means that I can trace back, and which means that A ER1 second plus B ER1 x prime plus C ER1 x is 0, which means that this is a solution. Right? And this is where a characteristic equation comes from. Now, in the second case, second case more complicated, and so in the second second equation, Cauchy on it. So you have a x squared y second plus b y prime plus c y is 0. Right? So if we guess that the solution is of the same form, this doesn't work, right? So if we guess that y is e to rx, right? So then a x squared e to rx second plus b e to rx prime plus c e to rx is 0. I explain again. In the case where a differential equation has all constant coefficients, the first guess is the solution has to be of exponential form, and you plug everything into the equation, you get ax squared plus ar squared, yes?
Should it be bxy prime?
Bx, yes, thank you. Can you sign back the paper, please? So you plug everything into the equation, you have ar squared plus br plus c is 0. So this equation has the advantage that you don't have x, right? And so you solve this equation and you find the form of the solution y. Now, the Cauchy-Euler case is more difficult because you have x squared and x here. If we guess that the solution is of the exponential form, I plug it here, right? I do the same computation. I have ax squared r squared e to rx, because this is this, plus bx r e to rx, because this is this, and e to rx is 0. So I put e to the x outside, right? Suppose that I guess the form solution is exponential of x. I plug it into the equation. So this is x second will be r squared e to rx, e to rx prime will be e to rx, and this is the same. Now I put e to rx outside. I have a as x squared r squared plus bx r plus c is 0, which means that a x squared plus c is 0. So this equation depends on x, and this is not a quadratic form. doesn't work, right? This is why in the Cauchy-Euler case, you cannot guess the solution to be out from exponential. All right? I explain again. Suppose that I want to solve this equation. I guess the solution is exponential of Rx. I plug everything into the equation. I get ax squared r squared plus bxr plus c times e to rx is 0. This guy is not 0. So finally I get this equation. This is not a characteristic equation because it depends on x, right? So we want something which is independent of x so that we can solve for the r. So what form of solution should we try next? Yes?
Y equals x to the power.
Yes, can you send the back the paper please? Right, so this doesn't work. So the next try is the following. The next try is that y is x to the r. And this time it works because when I take the first derivative is rx to r minus 1 and y second will be r minus 1 x r minus 2. Right? Right, so I plug everything back into the equation. I'm gonna get a x squared xr second plus b xr prime plus c xr is 0. Now I replace everything inside. I have a r minus 1 xr minus 2 plus bx xr minus 1 plus c xr is 0. Right? So what can you see from this equation? I explain again. So in the first, so I look into this equation. This equation is more difficult than this one because the coefficient has x squared and x, right? Exponential doesn't work. Now, I guess the solution is out of form x to the r. The first derivative, this guy gives me x to r minus 1, and the second derivative gives me r minus 1, x r minus 2. I plug everything into the equation, right? So this is y second, this is y prime, this is y. So this x r second give me r minus 1, x r minus 2. This x r prime give me r x r minus 1. So what can we say, see from this equation? Yes?
Well, so you have x squared and then you have x to the r minus 2 and that's x to the r times x to the negative 2 and it cancels out and then it also cancels out for the next term x and then x to the negative 1.
Can you send back the paper please? So you see that this x squared go with this guy and this x go with this guy, right? So what I guess r minus 1 x to the r plus b x to the r plus c x to the r. And this guy is 0, right? It's clear? Now I can group all of the x outside, right? So this gives me r minus 1 plus br plus c x to the r, and this is 0. Alright? I can divide x to the r because then r minus 1 plus br plus c is 0. Right? So and this is the characteristic equation that we wrote down. Why? Yes?
Because it doesn't depend on it.
Yes. Can you send back the paper, please? So this is the characteristic equation because it doesn't depend on x. Since it doesn't depend on x. All right. So this now you can you write this equation under the form. So this is ar squared minus ar plus br plus c is 0, and so this is ar squared plus b minus ar plus c is 0. So if we can find one such that AR1 square plus B minus AR1 plus C is 0, then AX square x to the R1 second plus B x to the R1 prime plus C x R1 is 0. So x to the R1 is a solution. Alright? It's good. This is why in the formula that I gave you before, you have everything in exponential, in polynomial, right? Explain again. The Cauchy-Euler's equation is more difficult than the second order differential equation with constant coefficient, right? Because if you try the first case, exponential doesn't work. The next case should be the polynomial, right? So you suppose the solution is of the form of x power something. You take this, the first derivative, this gives you x r minus 1. You take the second derivative, this gives you r minus 1 x r minus 2, right? You plug everything into the equation. So ax squared x r second plus bx x r prime plus c x prime x r is 0. So this x r second gives you r minus 1 x r minus 2. This x r prime gives you x r minus 1. This x r is the same. Now you observe that here you have x r minus 2, but here you have x squared. So you can group this guy with this guy. This gives you x r, right? Here you have x r minus 1, and here you have x. So you can group this guy and this guy. This give you x to r, and this x r is the same. Now I can factorize out all of these x r. So I have a r minus 1 plus br plus c x r is 0. I can remove x r, and this is an equation of r only and not x, right? So this is independence of x, which is good because you can solve this equation separately, right? So I can write out this like ar squared minus ar plus br plus c, because this is the development of this guy, and I can group this guy and this guy. I have ar squared plus b minus ar plus c is 0. This is the equation that I wrote for you in the beginning of the class. So if you can find a number r1 that solve this equation, then x r1 is a solution of the Euler-Cauchy equation, right? So this explains the difference between the two formulas that I gave you before. Questions? So basically, this is knowledge from the differential equation class, and we review everything so that you are safe, right? So the midterm will be like this.
When is the midterm again?
Sorry?
When is the midterm again?
Next Thursday.
All right.
Right. So let us. So I posted a practice exam online. So the practice exam will be the practice exam is exactly like what we did in class, and the midterm will be like this. So we have one problem, and of course it's going to be similar to this one, right? So let us try to practice a little bit. So, any questions on this Cauchy-Euler equation? It's good? Right, so let us try to solve this equation. You have to solve 1 plus x squared plus u second 1 plus x u prime plus mx is going to be 0. And this is on 0 e minus 1. And then you have u0 is going to be u of e minus 1. This is going to be 0. And the fx is going to be given by log of x on 0 square root of e minus 1 and 0 otherwise. Alright? Right, so we have to solve this equation. You have 1 plus x squared u second plus 1 plus x u prime plus fx is 0. So this is complicated, right? So, yes?
Is it all the square root of e minus 1 or is it just square root?
It's gonna be square root. I'm gonna explain later why we have square root. But, so this is the equation that we have. It is complicated because you have 1 plus x squared y second plus 1 plus x y prime plus fx is 0. So first we have to simplify this a little bit. Any idea how you can simplify it? Yes?
Can we use the form of the Strom-Louisville
Yes.
eigenvalue problem?
Yes. So, but this is a little bit different from what we did in class, right? So in class we did t squared, x squared and then x. So how can we transform? Here you have 1 plus x and 1 plus x. How do we transform back to the previous form?
Change a variable.
Right. Can you sign the back of paper, please? Right. So what you do is to change t to be x plus 1, so that it returns to what we did in class. Right? So you change t to be x plus 1. So in this case, you're going to have t squared u second. So then px plus 1 will be ux will be pt. Right? So here you have t squared phi second t plus t phi prime plus gt. Gt will be fx. So what is the range of t now? Yes?
-1 to e square root of e minus 2.
No, x is going, so,
My apologies, it'd be 1 to square root of e.
right, just add back the paper, please. So here I have x is going to be from 0 e to the power minus 1, which means that t is going to be from 1 to e, right? Okay. Right? And now I have to change the t. The gt will be gx. So the gt will be log of t minus 1 for 1 square root of e and then 0 otherwise. Right? So you have to shift the solution, right? So here I changed the variable, right? So 1 plus x will be t. So 1 plus x squared will be t squared. This u will be the phi in terms of t. This 1 plus x u prime will be t phi prime. And then this fx will be gt, right? So what is this gt? The gt will be exactly the same with the fx, except that I shift it to 1 square root of e. Right? So this g is different from 0, on 0 square root of e minus 1. And so I shift it, I just add 1 here and 1 here, so I have 1 square root of e. Right? Right. So now I can forget about this equation. I'm gonna solve this equation on t. Right. So we forget about this equation and we solve the equation on t. Solve the equation for t. So what is the strategy that we have? What is the operator in this case? Yes?
Should assume T to the R.
No, yes, T to I is to solve the eigenvalue problem, right? So the first thing that I have to write is to write out first step number 1, find the basis. How do I, yes?
Just a quick question. For GT, why is it not ln t minus 1 since t is equal to x plus 1?
Yes. LT minus 1. Yes, thank you. Thank you. Can you sign the back of the paper, please? Yes. So, yeah. So, yes, so probably, I think I make a mistake here when so it is log of x plus 1. Thank you. So, 0 square root of e minus 1 and 0 l squared, yes. So this is log of t, sorry. So there was a table in the beginning, right? So fx is the log of x plus 1. When x is 0 to e square root of e minus 1. So when I do the change of variable, it's going to be log t times 1 square root of e, right? Questions? Right, so we know that this is a kind of sum-living equation, so I have to find the basis so that I can expand the solution on this basis. What is the, so how can I find the basis for this guy? In general, how would you find a basis? You solve what?
Yeah, I can probably promise.
Yes, can you sign back the paper, please? So we need to solve the sum-living eigenvalue problem. Right? So you have to solve the sum-living eigenvalue problem. So you have what? You have L of phi is going to be lambda W. Remember that? And now we have to find no, not phi. It's not good. Find the basis, right? It's going to be of the form P x phi prime plus qx phi x. Right? So this is what we have from the previous class. You're gonna have to solve the sum-living eigenvalue problem, right? So you're gonna find PQ such that you can write this guy under this form. All right. So this L phi will be Px phi prime prime plus Q phi, right? Question? Now we have to find P and Q. It's clear? Right. So now you're gonna have L phi is going to be P prime plus P second plus Q times phi, right? Right, so and then I'm gonna put this to be lambda W phi. Right? So in the previous class, what was the form of W? Can I have the notes from the previous class? Yes. So problem was what? So So in the previous class, we consider this T phi prime plus phi. Let me change it. T is phi over T. Right? This is the problem that we considered in previous class.
Should be T squared.
No, this is the problem that we considered in previous class.
Oh, previous, all right.
This is the previous class problem, right? So, can you identify, can you compare the two problems and tell me the similarity between the two problems? This is the example in the previous class, right? So in the previous class, I don't use T, but I use this formula. Yes?
W would still be 1 over T.
Excellent. Can you sign the back of the paper, please? So in the previous class, I considered this problem. X phi prime prime plus phi over x is lambda phi over x, right? For this problem, I want to identify the stum-Liouville problem first. But in the previous class, we solved a similar problem, but which is x phi prime prime plus phi over x plus lambda phi over x. And now I change the name of the variable, right? So this is x. Now I change the name to t, and this phi is going to be phi, right? This phi will be this guy, and this t is going to be this guy. So this t is going to be this guy, right? So now I expand this guy. So I get t phi second plus phi prime plus phi over t is equal to lambda phi t, right? So now I multiply this by t squared, so I have t squared phi second or t phi prime plus phi is lambda phi, right? And so this is the operator that we have over there. Okay, it's clear. Questions? So basically, in the midterm, I'm gonna ask you something similar to this. I'm not asking you to change the weight to 1 over t squared. It's gonna still be 1 over t, right? So you try to understand this specific example, right? So now I'm gonna have, in this case, the p will be what? The p will be.
T squared.
Sorry. T, yes. T, and the q will be. No, the q is the one associated with this one.
Log T.
Yes, can you go sign the back of paper, please? This is going to be 1 over t, right? So then you're going to have what? You're going to have phi prime plus phi over t, and this is equal to lambda phi over t.
How do you know that Q is 1 over T?
Because here I have 1 over t is the coefficient of the extra phi, right?
Wasn't that the example from the previous class?
Right. So I just
Or you're still on that?
yeah, I'm still on this example, right?
Thank you.
Right. All right. So I'm still on this example, right? So in this case you have t phi prime plus phi over t is lambda phi over t. This is the stum-Liouville eigenvalue problem that we considered in the previous class. So in this case you have t, p is t, and q is 1 over t, and this is basically the one that we have from the previous class, right? Questions? It's clear, right? but basically, one thing that you can observe is that you can put Q to be 0. And here you still have lambda minus 1, right? So you can put this to this guy, and then the lambda will be lambda minus 1. All right? Is it clear? Good. You can follow it, right? So, all right. So I want to put it under this form, and I want to solve the eigenvalue. So I just want to focus on this single eigenvalue problem, so that you know how to compute that, right? And then this is going to, and then the W is always 1 over T in the exam. So basically, I transform this equation into this basis, all right? Right. So then we're gonna have so we solved the eigenvalue problem. So what we have is that you have 1 over T times phi prime prime plus phi over T is equal to lambda phi over T. Right? So that I can find a basis for this equation. Right. So now this eigenvalue problem can be written like T phi second square plus T phi prime plus phi is equal to lambda phi. Right? In fact, this guy doesn't matter, right? So I can put it to the other side. Right. So script. How do I explain this? So the coefficient here, right? So in the previous example, I have phi over T. So I put it to the other side, lambda minus 1, right? And I can call it lambda. Right? It's clear? Okay, so let me put it back to phi over T. And then here you have phi plus lambda phi. All right? It's good? Now, how can I solve this problem? Yes?
You have to make the characteristic equation.
Right. So, so the characteristic equation take the forms. Right, so it's going to be T r squared plus 1 minus lambda is 0. Why do I have this? Why do I have this 1 minus? Yes?
Because the T to the first term is going to be A minus B, or B minus A.
And BA
B
both
and A are
1.
both 1.
Yes, can you send back the paper, please? All right, so now you have this characteristic equation. Yes, so this is so case number 1. I don't like to put phi and the 1 lambda here. Can I just combine those two into 1, right? So I can, yes, let me combine it into 1. Because here I have lambda minus 1, right? And this I can put it to be theta. So this is theta phi. Okay, it's good. And so here this is theta. So that we don't have to deal with the 1 minus lambda. All right. So what I did is that here I have 1 phi and here I have lambda phi. So I just group them together and I have 1 minus theta, lambda minus 1. and I put that to be theta. All right? It's good?
Negative.
Yes, it's negative. Thank you. Can you sign back up paper, please? So case number 1, theta is positive.
I said negative.
Questions?
Oh, okay, no, I did it the other way around, so I got confused by the negative sign.
Right. So case number 1, theta is positive. Is it clear what I'm doing? So theta is positive. What happens when theta is positive?
Two roots.
Yes, they have to. Can you sign the back of the paper, please? So then you have 2 roots. 1, 2 is plus or minus square root theta. All right? So what happened if we have 2 roots like this? From the formula that we discussed before. Yes?
C1 and x to the root plus C2.
Can you sign the back of the paper, please? So you have phi of x is C1 e to the R1x plus C2 e to the R2x, and this is C1 e to square root theta x plus C2 e to minus square root theta x, right? Right, so the boundary condition here is phi 0, is phi e, and they're both 0.
Shouldn't it be phi 1? Because we're basing this off of the,
So this, you have 2 separate solutions, right? R1 is plus theta, and phi, yes?
right, but I'm going off of the boundary values.
The boundary is phi 1, yes. Thank you. Can you sign the back of the paper, please? So I have 2 boundary conditions, right? Now I'm gonna plug the 2 boundary conditions to the equation. Yes?
Since this is an Euler-Cauchy equation, should we be using exponents there instead of x to the r?
No, this is Cauchy-Euler, so you have to use polynomial,
Right.
right?
Yeah.
Yeah, shouldn't we add x to the...
Thank you, yes. Thank you. Can you sign back the paper, please? So you have x to the square root theta and x to the square root minus theta.
But should we be using T at all? Or not?
Yes, you use t. Yes. Can you sign the paper, please? So you have t. All right? Right? So now you're going to replace 1 into this equation. You have phi of 1 is going to be C1, 1 plus C2, 1. So this is 0. All right? So what can you say about C2? Yes?
C2 minus C1.
Can you sign the back of the paper, please? So in this case, you have what? You have C2 is minus C1. So now I'm going to have phi t is going to be C1 t to square root theta minus C1 t minus square root theta. Right? What is the next step? Yes, can you say the back of the paper, please? So you're going to use the second boundary condition, right? So phi e is 0, which means that C1 is square root theta minus C1 is to minus square root theta is 0, which means that C1 e to square root theta minus e to square minus square root theta, right? And this is 0, right? What can I say about this? Yes.
We know that the e square root theta minus e to the negative square root theta is strictly positive.
Why?
Because it can't be, you have one whole term minus a fractional term, and we know that'll be greater than 1 in this case. And so then C1 has to be 0.
Right. Can you say at the back of the paper, please? So this guy is always positive because we know that this is bigger than 1 and the other one is smaller than 1, right? So C1 has to be 0. So in this case, there is nothing, right? So there is no eigenvalue in this case. In this case. All right? Right, so I explain again. I look into the characteristic equation. There are two roots, plus or minus square root of theta, right? So which means that you have the form of the solution to be C1 t to R1 plus C2 e to R2. So in this case, it's a Cauchy-Euler-Cauchy equation, which means that here you have to use polynomial. So you have C1 t to the square root of theta, C2 minus square root of theta. I use the two boundary condition. The first boundary condition gives me C1 plus C2 is 0, which means that C2 is minus C1. So I plug C2 to be minus C1 here, so phi t is C1 t square root of theta minus C1 t minus square root of theta. So I use the second boundary condition. I conclude that C1 is 0, which means that in this case you don't have anything. Case number 2. Right? Case number 2. What happened in case number 2?
We have a double root of 0.
Let's get inside the back of the paper, please. So we have r squared minus 0 is 0, which means that r is 0. So what is the form of the solution according to the formula that we have before? Yes?
C1x to the R1 plus C2 ln x x to the R2.
Right.
And so then in this case, if it's R equals 0, you would have the x to the 0 term would just be 1, so you'd have C1 plus, and then C2 ln of x, and then that's it.
Thank you. Can you sign the back of paper, please? So you use the formula, right? So you just replace phi t will be C1 e to the 0 x, no, x to the 0 plus C2.
T to the 0, not x.
Can you sign the back of paper, please? I confuse with C2 log t, t to the 0. Right, so this gives me C1 plus C2 log t. All right? So you just use the formula that we have. So I always confuse between t's and x. So in this case, you have phi t is C1 t0 plus C2 log t t0, right? So you replace the exponential by the polynomial and the x, the t by the log t. So this gives me C1 plus C2 log t, right? So what is the next step?
Plug in the boundary condition.
Can you say the back paper, please? So I plug the boundary condition. So I have phi1 is 0, which means that C1 plus C2 log 1, and this is 0, right? So which means that C1 is 0, right? I plug the boundary condition. The first boundary condition is phi1 is 0. I plug 1 here, so I get C1, C2 log 1 is 0. So this guy goes away, so C1 is 0. So then phi t will be C2 log 2, log t. What is the next thing? Can you say the back paper, please? So now you use the second boundary condition. You have phi is 0, which means that C2 log e is 0, which means that C2 is 0, right? So in this case, C1 and C2 are both 0, so you have no eigenvalue. Eigenfunction. All right? In this case, because both C1 and C2 are 0, you don't have eigenvalue and eigenfunctions. Questions? I explain again. When theta is 0, so you have r squared minus 0 is 0, which means that r is 0. You use the formula. you have C1 T0 plus C2 log T T0. So the T0 is 1, so I have C1 plus C2 log T, right? I plug the first boundary condition, Phi1 is 0, which means that C1 plus C2 log 1 is 0. This is 0, so C1 is 0. So Phi2 is, so Phi T is then C2 log T. I plug the second boundary condition, I find C2 is 0. So in this case, you don't have any eigenvalue and eigenfunction. Right? Case number 3, theta is negative. Case number 3, theta is negative. So what happens when theta is negative? How many roots do we have? Yes?
You have to.
Right. Can you sign back the paper, please? So you have R1 and R2 that both the square root of theta, and this also gives me I square root of absolute value of theta. Right? Yes?
After we finish this example all the way through, could we do it as if like we did get C2 is equal to 1, so I like, just to refresh like what happens when we do have an eigenfunction for this part? Or like, are you,
for this
on
case,
the test, are you going to get, is it going to be 0 or?
on the
could it
test, it's
possibly
only to be 0. But if there's an eigenfunction, what eigenfunctions do you think it should be? According to your experience with the previous cases. Yes?
Because it would be a constant, we should take an arbitrarily easy one, so the function of 1.
Yes, can you send back the paper, please? So normally the first case don't give you anything. The second case, in the previous example, you see sometimes you get 1, right? So in this case you don't get anything, but if you get, it should be 1, right? So in this case, which means that normally C2 will be 0. So what you get is just C1 with a 0 here. And then you have one eigenfunction, which is 1.
Right, but what do you do at the very end of the whole problem if it is 1? If
You
we're
just add it.
plugging it again.
Yeah, no. So here you're gonna get something like cosinus n pi, and pi is x, right? Here you have 1. You group 1 and everyone.
Okay.
Remember that? So you remember the Fourier series, right? Fourier series, the last case gives you cosinus n pi x and sinus n pi x, right? And then this case gives you 1.
Right.
So you group everything and you get a Fourier basis, right? Other questions? Now, in this case, the two roots will be plus or minus I square root theta. What is the form of the these? Yes.
Constant 1x to the positive root theta cosine root theta over something ln of x, and then move to the other with the sign.
Okay, can you sign the back of the paper, please? So for this case, you're gonna get P of t will be C1 cosinus of square root theta log t plus C2 sinus square root theta log t. All right? Right. So in the the constant coefficient case, if here you have plus or minus square root theta, here you have cosinus t, right? Square root theta t, and then sinus square root theta t. But in this case, it is a Cauchy-Euler problem, so you replace t by log t. Questions? Yes?
Do you not do like C1x to the power of?
So the power will be 0, right? X to the
Oh,
0,
I see.
x to the 0. Other questions? Yes?
Oh,
Okay. So there's an x, but the power of the x will be the real part, right? So if you have 1 here, this gives you 1. All right? But here is 0. So it gives you 0. So x to the 0 will be 1. So you have C1 cosinus of square root theta log t plus c2 sinus of square root of theta log t. Because here x to the 0 and x to the 0 gives you 1. All right. So what is the next step?
Boundary.
Yes. So you plug the boundary condition into it, right? So the first one is phi1 is 0. So when phi1 is 0, you have c1 cosinus of square root theta log 1 plus c2 sinus of square root theta log 1. And this is 0, right? What can we say about this guy? Yes?
C1 is 0.
Yes, can you say at the back of the paper, please? So the log 1 will be 0, all right? So you have c1 cosinus of square root of theta times 0 plus c2 times sinus of square root of theta times 0, and this is 0, right? So sinus of 0 is 0. Sinus of cosinus of 0 is 1. So I have c1, this goes away, so c1 is 0, which means that phi t will be c2 sinus of square root of theta log t. What is the next step? Yes?
The second boundary condition, phi.
Can you sign back the paper, please? So now you plug the second boundary condition, right? So your phi is 0, which means that c1 sinus of square root of theta log e
Should be C2.
C2. C2. Thank you. Can you sign back the paper, please? So what happened in this case? Yes?
Well, the natural log of e just goes to 1, so then you know that sine of the square root of the absolute value of theta is equal to 0. So you set that square root equal to n pi.
Yes.
Isn't the boundary value square root of e though?
No, it's e. The square root is for the function. The function is defined from 0 to square root of e minus 1. But the boundary is from 0 to e. Right? So can you sign the back of the paper, please? So the function f I define is from 0. So the domain is from 0 to e, and the function is defined on this guy, and here is 0. This is ft. Square root is only for ft, and the domain is bigger than ft. All right. So in this case, log of e is 1. So sinus square root of theta is 0. Which means that square root of theta has to be n pi, and so theta is minus n pi squared. Theta is right. It's clear. Questions? It's good. Theta is minus n pi squared. So what is phi? Yes?
Sine of n pi log t.
Can you sign it back up paper, please? So phi will be sinus of n pi log t. All right, so I can put an n here because I have multiple value of them. All right. So so far what I solved is the following. I have solved t square of phi n plus t phi n is lambda n phi n. Right? So far what I did is that I found solution for this equation in which phi n is sinus of n pi log t, and phi n is minus n pi squared. Theta n, sorry, theta. Yes?
Should be phi double prime
sign factor properties. So far what we did is that we solve this equation. We have t squared phi n second plus t phi prime is theta n phi n, and we found that phi n is sinus n pi log t, and phi n is minus n pi squared, right? According to the theorem, all of those guys are orthogonal, but with respect to which weight? Yes?
1/t.
Yes, can you sign back at the back of the paper, please? Right. So we know that all of those guys are orthogonal. So phi n, phi m are orthogonal with respect to the inner product so you have FGW 1 over T is inner the interval from 1 to E of FT GTDT times 1 over TDT, which means that you have phi n phi m phi n 1 over t is going to be 1 of e sinus of n pi log t sinus of m pi log t 1 over t dt, and this is 0. All right. According to the theorem, all of those vectors are orthogonal with respect to the inner to the weight 1 over t. Right? And which means that if you multiply sinus of n pi log t, sinus of m pi log t, 1 over t dt, and you integrate from 1 to e, it's going to give you 0. Questions? It's clear? Right. So, so basically you have the basis, right? You have a basis. Right. So this is the Sturm-Liouville eigenvalue problem. Eigenvalue problem. And the basis is going to be sinus of n pi log t, which is nothing but phi n t. All right. So far what we solve is this Sturm-Liouville eigenvalue problem, and once you solve this Sturm-Liouville eigenvalue problem, what you obtain is a basis. Sinus n pi log t, which is the eigenfunction, right? And all of those functions, they are orthogonal with respect to the weight 1 over t. All right, so which means that when you multiply phi n and phi m, and you multiply the product with 1 over t, you integrate from 1 to e, they are orthogonal. So the integral will be 0. The condition is n is different from n. So basically what you did is you establish a basis. And this basis is going to be the basis of all of the continuous functions that you can think of, right? So we can continue on Thursday. Any questions?